Welcome back to the webinar series of MetaMAT. And today we have the immense pleasure to welcome Professor Gianluca Memoli from the School of Engineering and Informatics, University of Sussex. And so you can watch the biography of Gianluca on the website. It's a lovely biography. So he has a background in physics engineering, but he comes also from the National Physics Laboratory. And one thing which is really great is that he holds an academic and an industrial position as the CEO of a startup company specialized in metamaterials. So today, Gianluca is going to talk about bridging metamaterials to creative industry and hospitals, which is a fantastic subject. Professor Memoli.
Ready to go. So thanks for everyone for having me today. Today I'm traveling. I'm in Manchester. So if some of you are here around, maybe we can go to the pub afterwards. So I decided to tell you some experience, to share with you some experiences, some of my experiences on transforming metamaterials into applications. So the story starts from this screen, which, well, raise your hand if you are not familiar with it. It's a black screen, there are some words on top, and then there is a fantastic sound. And if we listen to George Lucas, audio is 50% of the movie-going experience. And this story of the 50% also repeats according to market research in metamaterials. So I put here some numbers from some recent market research, which tells you what is the value or the projected value of metamaterials from 2021 to 2026. Now, at the moment, a lot of this money here is due to electromagnetic applications, mainly antennae, radar, beam steering. But the point is that all the projections and all the reports that you see say that from now on, acoustics is catching up. So in 2026, half of this is expected, or in 2030 even more, half of that is expected to be acoustics. What does that mean? That means that there are a lot of applications for metamaterials in acoustics, and here we as a community are developing them. And so what we did, so I chair the UK, so the special interest group in acoustic metamaterials of the UK Acoustic Network, and now it's shared with the UK Metamaterials Network. And what we did in 2019 is we asked our members. Can you hear me? Yeah? Great. So in 2019, we asked our members what are the applications of acoustic metamaterials. So we did a proper survey, we asked the permission, we did the ethics approval, and this is what came out. So what you see here is a word cloud, which tells you what. So the larger is the word, the larger, the more often it appeared in the survey. And so if you let me try to summarize that, there are three key applications there. One is sensors for inspection, and that can be NDT, for instance. The other one is noise management, and the other one is directing energy. And in my opinion, this is the one on which we are somewhat all working on, because either is waves in plates, or earthquakes, or waves underwater, or sound in air. We are all trying to direct energy in ways that were not, how to say, simple to think about. So before I go into my talk, so what I'll do today is I'll present to you some applications into this part here and into this part here. Now, before I go into that, let me tell you some key considerations. So, for me, working in acoustic metamaterials means that you start from standard materials, which can be wood, plastic in this case, or metal, and then you add engineering and design, and you get something else. And you can say that you have objects which have negative mass. I say that you have objects which have an index of refraction or the equivalent of it, which depends, which is parallel with optics. You can say that you can build bands and describe your material in that sense. But from the point of view of the applications that we saw before, there are two outputs there. One is noise cancellation, and the other one is sound manipulation. So all the metamaterials that I will present today were built using a 4-bit quantization. What does that mean? It means that like you have 26 letters to make any words in Scrabble, we use 16 basic shapes to make all the metamaterials that I will present to you today. So the process then of designing a metamaterial is give me a bandwidth of interest, give me a size available, and then pull it up, turn a knob, and out comes out 16 shapes that then you can reassemble like if they were Lego bricks. Now, one key point is the role of thermoviscous effects. So this is something that we addressed at the start. And if you look at here, the black line and the dotted line, this compares. So this is a COMSOL model, and this relates to one of the bricks that we presented in the paper in 2017, which went on Nature Communications. Now, the 2D model, and as you can see, there is very little difference when you put the viscosity into that. These were bricks which were very, very small. So you would expect that the thermoviscous is determinant there, but it's not. And in fact, those bricks allowed a transmission of 99% of the sound going through. But crucial for the modeling side and for the simulation side in COMSOL is the fact that instead, when you pass from a 2D model to a 3D model, you can see that the spectrum changes. The resonances, which before the jump of the resonance from this resonance here to the next one, is much, much higher here in 3D than in 2D. So this pushed and changed the way we do modeling at Sussex. From then on, we just used 2D models to shift a bit, to have an idea. And then all the modeling and all the, when we eventually designed metamaterials, it's all based on 3D models. The other thing that you notice is this shift of the peak. Can you see that? So this effect is much bigger than the one due to thermoviscous. And that is one of the key points that you need to take into account in using our bricks to design metamaterials. But for the purpose of today's, just let's say that this has been taken into account. So what I present to you are simulation results with 3D envisaged models. There is another issue there. How do I actually measure? How do I compare with the simulations? And that is a key point, in my opinion, if we as a community want to go to applications and convince people that metamaterials are really the best ever. Because we need to compare with what is out there. And what is out there is all measured through ISO standards. So, but then if I take a metamaterial, and so let me close my phone there. If I take a metamaterial and put that into an impedance tube, not all the metamaterials would actually give a proper response. Because some of them are based on interference, some of them are based on resonance which are perpendicular, some of them are based on resonances which are along the line of propagation, some of them are based on active materials, like a vibrant membrane. Are we sure that the ISO standards work in all the cases? Well, I'll let you take your decision on this, and maybe that is something we can discuss at the end. The key point is that talking with different people in different standardization institutes in Italy, in the UK, and also in other countries, it seems that it might not be the case. And in fact, there is not a generalized way in which people compare the performance of metamaterials or the metasurfaces that they design, which works all over the place. So in this talk, I'll use two methods. The first one is based on microphone scans. So what you see here is a speaker on the left-hand side, then there is a waveguide, then there is a metasurface that I put in between, and then there is a microphone here. That and you can see that it's mounted in a 3D printer setup that allows me to do a 3D scan. The other one that I will use is instead, and so that one is in the frequency domain, because what I can do is I can send tones and check what is happening. In this case, instead, in the other one, this is a measurement done in the time domain. And so what I can do is I can send a pulse, or I can send white noise, or I can send something which basically contains more frequencies. And with using the fact that I have two microphones and the transfer functions from one to the other, then I can characterize metamaterials. Now, obviously, this becomes essential if my metamaterial is a reflective one. So without further ado, let me talk about metamaterials for directing sound. And let me start from this. So in my, when I was at Imperial, as I had just arrived in the UK, I was doing theatre in pubs. And I had the chance to direct a play at the Imperial Drama Society. And what happened was I realized that I was extremely powerful as a director in terms of light. Because I could ask to my light technician whatever. I could ask directed light, diffused light, light that followed characters. But there is not such a thing for sound. Not if I don't spend an incredible amount of money to have a set of speakers that on which I can control singularly, or basically a phased array, that allows me to create interferentially different spots that move. There is some technology going in that direction, that we have now sound bars that track you when you are in the area, and the Southampton ones, for instance, are very strong in this. But let's imagine for once that we had a tool in which we could create sound effects, localized sound effects, like we do with light. So imagine that, that this image here becomes something that you could visualize with an acoustic camera. So if you could do that, how would the future look like? That was the question that I started working on at the start of my fellowship in 2017, 2018. And I want to show you a little bit of that, because creative industries, which have suffered a lot during lockdown, are a great part of our society. So we started using parametric speakers. If you don't know what a parametric speaker is, it's a speaker based on ultrasound, beam, and the nonlinear effects in air, which allows you to add up sound that you can hear. And what we did is we built a mock-up of a dashboard of a car, and we used metamaterials here on the speaker to send two different sounds to the passenger and to the driver. Now, let me see if we can hear the sound from this one. What you see here is a directional speaker, which is circled in yellow in the middle. And I'm using a single frequency here. And you can see that when you are in front, the sound is very strong. And if you are not wearing headphones at the moment, all the people around you are looking at you badly. Now, what happens if I put a metamaterial in front, so, which is actually circled in red in this case? So now, when I go at the front, there is nothing. But when I go to the side, here is my beam again. So parametric speakers have a very narrow bandwidth, so it's very easy to play with their emission. The problem is that if you stay in the beam of a parametric speaker for more than 5 minutes, typically 10–15% of the people there get an headache. We tried that. So trust me on this. So we need a different solution. And this pushed us a line of research that has produced different devices over the years. And I'll tell you very quickly about them. So the first one was, okay, so if we can treat sound like light, we can do a metamaterial lens, and we know that. But what happens if I put the metamaterial lens so that the focus is in the source? What I get, so if I collimate the emission of a speaker like I would do with a laser source in light, what I get is an emission which eventually becomes in a corridor and goes far away. And what you can see here is that we managed to increase the emission in a very small, so the blue line is the standard emission, and the red one is the one with the material lens. And this allows us to go further away and also to increase at a fixed distance the sound in a small angle. Basically, I transformed this speaker into a directional one. in real life, we don't use a single lens, we use multiple lenses. And what we did, in fact, was to build the equivalent of an auto-zoom objective for sound. And so we have two acoustic lenses here of the same focal, and what we did is we adjusted the distance. Why could we do that? It's because we found, through COMSOL simulations and measurements, that actually the law of thin lenses, which says that the inverse of the distance between the lens and the image plus the inverse of the distance between the lens and the source is equal to the inverse of the focal length of the lens. But also, if that applies, then you can add two lenses and make a system of lenses. Does it work? Well, according to COMSOL, yes, it did work. According to measurements, yes, it did work. But could it be perceived as such? So this is our device. The motion is exaggerated for the purpose of the movie. And what we had is we had the camera, which was tracking the face of the person, and eventually was adjusting the distance automatically. So according to our calculations, this created a small ball of sound that moved with the person as the person was moving. Imagine that in a crowded area. Sound without headphones, you could call it, as if you imagine that a newspaper headline. Does it work? So to do that, to check whether it worked, we mounted a speaker into a box, we put a lens at the front, and we moved the second one, and we mounted all of it on a rotation table that we did in-house. And if you are familiar with home electronics, you can recognize some Arduinos around the space. So what we did then is we took a very large room with very few obstacles in between, and we paneled and we put on the floor different targets like this. And then we asked human volunteers to tell us where they felt that the sound was being delivered. So basically, I was setting the sound to be delivered in the first cross, and then I asked the person to find the cross where the sound was delivered. Now, we got then in this way, the preliminary study got us some histograms like those here, and what you see here is the distance from where, well, in this case we used the Kinect that you can see on top to decide where we wanted to send the sound. And so this is how good it was. And so you can see that most of the peak are at zero. Most of the answers are there. Now, the numbers are low, and you're right in saying that. But if you look at the standard deviation of all these answers, then you get that we were right in delivering within 20 centimeters. Now, we were using sound. We were actually using, for this experiment, first we started with single frequency like the one that you heard in the previous one, but then we realized we became better at designing metasurfaces, and we managed to pass through a guitar solo from YouTube. So what is happening with this research now? What we are doing now is, since we are getting very well at delivering sound and at designing metasurfaces which cover a larger bandwidth, then we actually have designed the first speaker which mounts metamaterial in front. Metamaterials and speaker is not new. There is a company, a UK company called KEF, which has produced last year in the middle of lockdown, has launched a speaker which has at the back a metamaterial absorber. And what we have done, and in that case, they reduced the back emission of the speaker. What we've done is we have complemented that with something that enhances the directionality of the speaker. And so now we have the first speaker that actually can deliver sound very precisely to a person. And if it's a movable person, at least along a line, then you can have personalized sound cues to a person in an audience. Imagine that in a concert. So you're playing, and suddenly you have a specific conversation with a part of your audience, specific musical conversation. Imagine that in a video game, and suddenly you imagine that the headphones that I'm using now are probably no longer necessary. What you need to know, however, is how many points you need to deliver, which is a key question in the entertainment industry, which has brought us the Dolby Surround, the Dolby Atmos, and many other ways of delivering sound for immersive experiences. So the frontier then, so there is a space in the frontier for sound, which is for metamaterials. But then lockdown arrived, and at that time we had realized that there were some combinations that cancelled sound. So in this grid here, what you can see is that some of the bricks are empty and some of the bricks have a channel. And if the ones which have a channel actually creates a delay of 180 degrees, then I'm using the same trick that we use for headphones, but potentially over a larger scale. What I'm doing then is I'm using a cancellation trick to cover a large area without using an active method, which instead is what is fantastically working these days, for instance, in aeroplanes. So why we go for a checkerboard design? And to give you an idea, I have picked this video on YouTube, and we are going to minutes, so this is from UPenn, and we go to minutes 2:11 there.
These are very poor radiators of low frequency sound.
So did you hear the reduction there? I hope you did. And you can see that depending on how you mount them, you can pass from a dipole to a quadrupole. So a quadrupole then becomes an interesting object if you want to do noise cancellation. So as I was saying, in the middle of lockdown, we were thinking about, we had just discovered that there was a possibility of some combinations that could reach noise cancellation. And then, do you remember those days when we were clapping at 8 o'clock for the heroes in our hospitals, which were fighting the war against COVID? Well, it was in one of those evenings that I remember that actually I had made a study in 2014 where I had found that actually in intensive care units they had already too much noise. So us clapping would not help. Maybe instead reducing the noise or finding a way to filter the noise could help. And this is what we did as a team during lockdown. It was, if you want, our way of feeling that we were doing something against the war, in the war against COVID. So let me tell you why. So there are guidelines from the World Health Organization which tell us that the typical sound that you should expect, the typical sound pressure level that you should expect in a hospital is 35 dBA. If you're not familiar with the A, that is a weighting that takes into account, allegedly, an average here, filter sound. Not a great one, but hey, this is what you find in the literature typically. So, but if you think about that, that is the sound that you find in a library where there is always someone telling you to be silent. And in fact, maybe more practically, the US guidelines are a bit higher, and now there is an NHS one which is equally a bit higher. How much do we find instead? So there was again, during lockdown came out, not this year actually, this year came out a review of all the studies made in hospitals measuring noise levels. And well, what they found is that the day one goes from 37 to 88, and the night one goes from 38 to 69. It's not a surprise that intensive care units or hospital wards which have been transformed into COVIDs have been defined as a hell. Now, imagine, to give you an idea, this is like having a vacuum cleaner close to you at 10 feet from you on all the time for how much you are trying to sleep. Not very much for sleeping. And in some cases, it can go much higher, up to a rock band noise. So how could we do about that? What could we do, we wondered. And so what we did is, you know that there were times, small between the different peaks of the pandemic, there were times when we could go into the hospitals and actually measure something. And in the collaboration that we had with the clinicians in Brighton and London, these were the moments when we went there to measure. And so this is the sound of a CPAP machine, which is an help to breathing. Can you hear that? That's the typical noise that you have from an air duct in a conditioning unit, only pushed a bit higher. If we go to a ventilator, which is a standard machine that probably no one knew about before the pandemic, if we push that instead, you hear that the sound due to the air is much lower, but the ventilators have a very specific object, which is there. Can you hear that? That is an alarm. Now imagine that you are in a place where there are many of these ventilators, and what you get is a lot of alarms coming from all over the places. And now alarms are essential because they call the nurses to go and check. But if there are too many of them, or if you also get the alarms that you don't want, then they become, from sound, they become noise. So let's see how much we measured. So based on what we measured, and we'll see that later, if you take 10 ventilators in a room, then you get 73 dBAs and 68 dBAs. And if you measure along the M25 motorway, which is the motorway which goes around London, which is very tragically famous for its noise, then you get 75 and 69. So in a hospital then you can get noise levels as loud as along the M25 motorway. In fact, the clinicians who were part of this study told me that they couldn't actually talk. And how can you deliver care if you cannot talk? And if they could not talk or they had difficulties talking, what about the patients? Why I'm worried about the patients? Because in addition to sleep disturbance that I imagine everyone can imagine in such a context, there is a clear evidence that noise produces an increased heart rate and an increased blood pressure, which then means that patients need to be sedated. And this typically eventually is one of the causes which brings a delayed recovery. During the pandemic, there was even someone, well, we're still in the pandemic, during the peaks, or last year, I should say, there was someone who even hinted that there might be an effect of noise on the stress of staff and the increased rate of burnout. Now, what you see here in this graph is the result of a questionnaire survey to the NHS, which is the UK national health system. And you see that the percentage of respondents feeling unwell and so having to take a day out increased. But that's not enough to say that it's due to noise, unless you go and read the answers. And what you see in the answers is that noise is increasingly becoming a word cited, just like in the word cloud that I used earlier. It's not new, because even Florence Nightingale used to say that unnecessary noise is the most cruel abuse of care, which can be inflicted both on the patients and the staff. So the fact that there is noise in hospital, or that there is something that is an issue to fight against, is not new. So why haven't we done anything? Well, because it's difficult, because there are constraints which make it very difficult to use traditional systems. So, but we are acousticians, are we not? So let's look at the spectrum produced by the ventilator. And what you see is that there is a background noise, and you heard that, and that goes higher as you go lower in frequency, and then there are the alarms. And you can see that for the ventilator in particular, the alarms can go as high as 25 dBs from the background. And they are focused, so there is a 1 kilohertz, there are the harmonics of 1 kilohertz, and then there are these objects here which are the da-da-da-da-da. So these are objects that you put a wall, you put an absorbing material, especially the high frequency noise is very easy to work with. But the point is that whatever you do, so this is a typical site in a UK hospital, the situation is crowded. There are instruments all around, and staff needs access to the patients with very short notice. So whatever you do, you need to have it movable. And also the patients should not feel as in a coffin, because as you can imagine, that's not something you would like in an intensive care unit where they are fighting for their life. But that was the strangest requirements that we received, which was they need to be cleanable with a wet wipe. And these are very difficult to achieve with traditional absorbing materials. Metamaterials maybe can do the trick. So what we did is we designed different series, different types of metamaterials based on the idea that I expressed before. So the phase cancellation idea. So the first one is, let's maximize the air through. So we designed the grill like this, and we found that this was a very resonant device. And you see here two different types of grills optimized for taking one peak only or two peaks if we could. These objects are potentially transparent. The measurements that you see here come from microphone scans, and you can see that they are very peaked. And they are very light, obviously, because I haven't added mass as I would have done in traditional solutions. I have taken it out. And we imagine these solutions to be mounted around the equipment. But then this would need the involvement of the manufacturers, or also this would involve something that you can open and close very quickly. So no, we said, too complicated. Next bit, let's go with something which has less air through, and that is the minimum requirement in these conditions. And what we found is we created a panel like this, which, as you can see, is made of acrylic, is transparent, and it has different paths in it to create the interference. And obviously, the paths are optimized to cover as much frequencies as you can. And what we did is we mounted this in a window frame, and we measured that with the ISO, which we asked actually an acoustic consultant to work with us, and they measured the performance with the ISO that they normally use to measure the performance of windows or parts, facade parts of a building. What you can see is that when you have the metamaterial here, and compared to when you don't have it, there is a clear net effect at all the frequencies. So we imagine, okay, however, the problem is that these are heavy, so they cannot be moved. So they need to be mounted fixed. And so this is a solution which has been proposed by a German study in 2016, only they didn't have the panels that could do it. So now we do, but maybe it's not what our clinicians wanted. So what we did then is we tried another solution, which is maximizing the transmission loss. Transmission loss is defined the pressure in the sound pressure level compared to the one without the metamaterial. So we went for something which does not let air through. It's broadband, it's half-transparent, and the measurements that you see here are done by microphone scans, which means I average the pressure over that I measure over an area to take into account potential reflections, and then I compare along the same area without the metamaterial. So this is an intermediate weight, and he has a performance which is quite significant, but he also has some dips. Can you see them? Now, it blocks the 1000. It does not really block the 2000s, does it? That is strange, because when we tested it, we found that actually it was working better. So what we did is we used different methods to characterize it, and also we did a COMSOL simulation to see whether actually we were understanding what was happening. And the idea was to take these panels and mount them on wheels so that they could be moved if needed. So what you see here are the results of different theories, or actually a theory, which is the mass law applied to 1 millimeter of artboard. Then there is the COMSOL modeling, and then there is the microphone scans and the pulse scans. You might also notice that the COMSOL modeling, the COMSOL simulations is on a different scale because it was translated upwards, and we'll discuss why maybe later in the questions. What I want to show you is that both the COMSOL the measure, the actually second peak. All the methods pick this area here, yeah, but there is a decrease into what is measured at the end. Now I saw something in the chat, so I'll go and see what was happening. No? No, not sure. Okay. So I had a message saying that there was some issue with what I was presenting. So let's go on.
It's all good, don't worry.
So these are point measurements, and this is an area or a line measurement. And you can see that high frequency, they differ very much. So they are good to predict this, but they are not good to predict what is happening here. And you can imagine that because the cells that we used end up with 1 millimeter of PLA, it's very difficult that they drop like this. So there is a question of what is the best method. Or if you want, there is a need to discuss what is the standards to use to characterize our metamaterials. But for the purpose of what we wanted to do, which was trying to give relief and respite to people in hospitals, maybe this is an academic question. So what we did is we mounted our metamaterials into a rack, and we covered that with a fabric that could be cleaned easily with a wet wipe. Now, what is the effect of that on the performance of metamaterial? Obviously, we had to run completely different COMSOL simulations to take that into account and to adjust the cell to take into account the fact that there was now a membrane in front of it which was participating to the effect. And then we assembled everything into a panel like this, and we brought it to a COVID ward. So in this particular hospital, the COVID wards were mounted by, so they took a part of the intensive care unit in this case, and they mounted walls, artificial walls, to separate one patient from the other. And so what we did is we mounted our panel here between the patient and the equipment, which was either, in this case, is a CPAP machine, or it could have been a ventilator. And then what we did is we mounted a microphone, well, a sound level meter, a class 2 in this case, one, in the position where the head of the patient could be. And we also added the second bit, so I mounted it this way to take into account that typically there are some additional reflections which increase the level that the patient feels. This was one of the outputs of a study which we did in 2014. So what did we get? So we had two sources, the CPAP machine and the ventilator, and what we measured was the sound pressure level over 1 minute in different conditions, without the barrier, with the barrier close to the bed, with the barrier close to the equipment. Now, because a barrier is more effective as it's close to the equipment, you can see that the levels that you measure on this side are always lower than the ones that are here. We also measured LA max, so we tried to pick with the maximum level in the 1 minute the effect of the alarms. So what do we see? That if we go for the CPAP machine, this one and this one, well, there is basically a 2 dB reduction. And if we go at the LA max, there is just 3 dBs. Not very effective. 3 dBs is the minimum to feel any difference at all. But if we go for the ventilator instead, where we tried to position our metamaterial to destroy the peaks, if you want, while here there is an higher component at low frequencies, then the effect is greater. We get 12 dBs in Lmax. No, sorry, 12 dBs in the sound pressure level averaged over 1 minute, and a bit less in LA max. So to understand what was happening, I actually, we did well, we put all the people in the room eventually took a turn on the bed and noted down what were the sources that we were hearing. Now, if we go back here, do you remember this peak down? So the emission of the ventilator at the peak here, at the peaks there, but you also add a peak here. And that is the thing that you could hear when you were on the bed. So the reduction that you see here is, if you want, half. So if you go from here to here, there are 4 to 5 dBs, which is half of the energy. Half of the energy was at 2000 Hertz. So if we want those to be effective to actually produce a relief to the people in hospitals, at least from the ventilators close to them or not close to them, which is probably more important, then we need to do better. We need to translate this a bit down while maintaining this bit. So in conclusion, I absolutely believe that acoustic metamaterials might play a key role in our society. If you consider the fact that you can design and think and imagine acoustic metamaterials as a design tool, then this can augment existing acoustic technologies massively. But what we need to produce as a community are more case studies. And these are essential if we want our technologies to make a difference for the people all around us. Or as my supervisor during my PhD was saying, if you want to explain to your grandma what you actually are doing. So thanks for your attention. Well, I have to say that Metasonics is looking for a physicist or engineer for 1 year if you're interested in spending some time doing products. Otherwise, please ask questions and I will be happy to answer. And thanks again for the honor of being here today.
Thank you very much, Gianluca, for this inspirational talk. So people, please ask some questions.